This paper was given at the American Physical Society March meeting. It is about the Quasi-Bragg law. This is a new law of physics with measured metric, with three-dimensional indexation, and with the structural solution for quasicrystals. Notice that in questions of science, the authority of 8,000 is not worth the humble reasoning of a single individual. Bragg's law transforms a crystal into a three-dimensional reciprocal lattice. This section applies to the matrix phase of melt-spun aluminium-6 manganese. For the quasicrystal phase, the geometric diffraction pattern is transformed by the new Quasi-Bragg law into a hierarchic structure. In this structure, an icosahedral cluster is made up of icosahedral unit cells. The unit cells are edge sharing, not face sharing as in the crystal. And the structure is infinitely extensive, uniquely aligned, and uniquely icosahedral. The unit cells have this property, that the ratio of the length to the edge width is the magic number tau, and this is constitutive for the geometric structure. The quasicrystal diffraction pattern is often called Bragg diffraction and Fibonacci series, but it's not Bragg diffraction because the orders are wrong, as you can see, and it's not Fibonacci because the ratios between consecutive terms do not vary. They're a constant value, tau, and so it's a geometric series. And anyway, Fibonacci series and Bragg diffraction are contradictions in terms. So let's look at the indexation. The indexation is pinned by the quasi-lattice parameter, which corresponds to half the length of the unit cell. We'll look at that in greater detail in the next slide. The indexation is geometric, three-dimensional, simple, and complete. Every beam has been indexed. The unit cell is made up of 13 atoms, extremely densely packed. And there are three principal axes, the two-fold 100, the three-fold 111, and the five-fold 201. And we'll look next at the stereographic projection of those three axes about the five-fold axes. They're contained inside a circle which includes the full 4 pi steradians of a sphere. And the indexation is geometric, three-dimensional, simple, and complete. With this complete indexation, we're able to calculate structure factors by conventional means. In this case, we use a supercluster order 6 with 100 million atoms. And the first point to notice is that the Bragg condition occurs on track 1. The structure factor is 0, all structure factors are 0, there is no Bragg diffraction. But when you scan off the Bragg angle, the quasi-Bragg peak pops up at the quasi-Bragg angle. And as a computational fact, it pops up at the same condition for all quasi-Bragg peaks. And the intensities of these quasi-Bragg peaks match experimental value very well indeed. Extraordinarily well. And the difference between the quasi-Bragg angle and the Bragg angle gives a measure of the metric. Well, what is the metric? We can illustrate that as follows. Consider a quasicrystal oriented to a particular condition and plot the populations of the various diffracting planes in a cluster. Then overlay a quasi-block wave. Well, what is a block wave? Consider a crystal at a Bragg condition with the zero order beam interfering with a Bragg diffracted beam. The interference causes a block wave. Then calculate the overlaps of these populations with a quasi-block wave, and the answer is given on the left. Do the same for two waves at Bragg conditions, pseudo block waves. They're pseudo because they don't exist. The overlaps are much smaller, and the difference goes to extremes as the cluster size gets larger. We saw an example of that in the last slide. The metric is fundamental for all wave phenomena and for all interactions with quasicrystals. There are many consequences I give you too. Notice firstly that the atomic planes do not occur at the same positions as the peaks in the quasi-block wave. And this tells you that it is impossible to image atoms with high-resolution transmission electron microscopy. Likewise, it's impossible to do accurate structural analysis without the use of the measured metric. More accurate is R2D focused phase contrast microscopy in transmission electron microscopy. In this micrograph, every atom is specified, located, and measured for size for the first time. Well, what is our conclusions? We do not ask, what is a quasicrystal? No one knows. We find that with edge-sharing unit cells, with three-dimensional indexation, and with the measured metric, the structure is complete, hyperspace is redundant, and a new physical law is described. Well, the first question asked at the meeting was, why has this not been published? And the answer is that referees are political, the journals are either inept or intellectually corrupt. And anyway, what can you make of a high school that eats its breakfast every morning in 6 dimensions?